some reason it doesn't.
But can I just control the? Let me turn the page.
Yeah, you can use that then.
Oh, okay.
That's the only option.
The only
Sorry about
option.
that, I don't know why it doesn't do it. Whenever you're ready.
Okay. This is the presentation of our proposal. Our topic is the characterization of stochastic gradient and mirror descent method. This is a collaboration work with me and Pei Datian. So we'd like to have some brief introduction into this topic. So generalization is a very important topic in machine learning. And usually people think that the generalization performance of learning system depends on the complexity of the model, which can be generally characterized by the number of the parameters you use. But so a new idea is that actually the learning algorithms you employed can also determine the generalization property of your learning system. So normally it is impossible to explore the whole parameter space. That is, it is impossible to sweep over all the local or global minimums. So actually you are only targeting at some of those local or global minimums. And this subset could be a good initializer, can be served as an implicit regularization for your learning algorithm. That is the idea of how these learning algorithms help generalize well. So suppose we have a model F and a data set Z that is defined in this sense. So we have some noise VI. So notice that VI here can either be the measurement noise or be the model noise. That means the model fails to capture some of those data in this data set. That could happen because your model cannot be very powerful. So we usually define training loss of this kind, which is induced by some loss function small l. And in the overparameterization case, what will happen? We generally assume that there's some data interpolation pattern behind this model. That means this set W is non-empty. This is a very general assumption for the overparameterization case. So if we define d psi like this form, this is very like a Bregman-like divergence. If phi is strictly convex, then d psi is a Bregman divergence. But if psi is not strictly convex, it is not a divergence nor any of those like probabilistic metric or discrepancy. However, if we let Wi to be the learning track of the learning algorithm, so Azizi and Hasibi in a recent paper, they proved that in the overparameterization case, they formed this learning algorithm into a minimax problem, and then proved that if this is the divergence dl of W and Wi plus 1 is non-negative, then we will have a convergence to this set W. And if this divergence weakly depends on W, its first component, then we can show that actually there's an implicit regularization. That means actually SMD is actually finding the closest point in W to the initializer in the sense of d psi. So in general, however, the loss is not convex because as we can see, here the loss is defined in this kind. Also, this small little L is a convex function, but F is generally very highly nonlinear, and therefore we have no convexity for this function. However, an alternative requirement is that DL could be convex in the neighborhood of W, and depends weakly on its first derivative, its variable. Sorry. And if we assume that Wi is close enough to W, these two assumptions is enough to have those convergence and implicit regularization property proved in that paper. So here we would like to ask the question is that for which class of loss function L, we can guarantee that we have this bound for Hessian and for all W. Of course, we cannot prove this for general W, otherwise L could be a convex function and everything is very straightforward. So we would like to add this constraint such that this loss L or this W is very close to the space W, capital W. And this is of course still a hard problem, but luckily we have a lot of progress or a lot of convergence analysis for SGD recently. So there are 2 more papers, and actually there are a lot more about the convergence of SGD. And of course the convexity is, we want to analyze the convergence for SGD, convexity is inevitable. So we would like to conclude the best convexity result from literatures and analyze the convexity problems for the simple cases and find out its difficulties. And we would like to conduct some more numerical experiments on those classic problems to examine our assumptions. So this is our schedules and goals, and I think this is all for my presentation. Yeah, thank you.
Any questions?
Yeah. Oh, yeah. This question. Yeah.
So guys, I want to make sure that we get to everything. So as the last speaker presents, if you're next, can you go ahead and get ready as they're wrapping up? And also, I'm going to be timing this to make sure that you guys, we get to everyone. So keep your eyes on me as you're presenting. So I'll try to give you a signal when your time is running out. So just remind you everyone has 5 minutes. Yeah. Thank you guys.
Thank you, sir.
You could also scroll.
Yeah.
How does it put on this?
Okay. So,
Would you please use the mic?
is it fine if I just talk loudly? Yeah. So, we're good. Okay. So my name is Akshay. This is Michelle. We're working on a deep reinforcement learning application for object recognition for reinforcement learning. Our mentor is Huang. We met him, and we're trying to discuss how we can just view the general idea of object recognition with CNNs with reinforcement learning paradigms. So it's just a brief introduction. The intuition that we're trying to exploit with our with the reinforcement learning algorithms is just the notions of active scanning and attention in neuroscience. So we're just trying to use the fact that adjacent features and images are useful in order to find certain useful characterizations of what's in them. So now I'll let Michelle talk a little bit about some of the prior approaches that we found in our literature review.
Yeah, so things that we kind of looked into are various reinforcement learning experiments regarding spelling correction, machine translation, and image captioning. A lot of different researchers used actor-critic frameworks for this task, and they took the actor network and conditioned an RNN for prediction, and then the critic network does policy evaluation to maximize different metrics for sentences. Like this is in the image captioning case. They used like blue as one of the metrics. And so we want to explore this application towards object recognition. Kind of the problem formulation for us is we want to take an image looking only at like some small window of the image, so restricting our agent to like only look at a certain range and masking out the rest of the image and starting at some random location. Basically, the 4 actions we can take are moving our search window like up, down, left, and right. And at each time step, outputting a probability distribution over which is like the step that we want to take next to try to basically optimally uncover as much of the image that we need to classify it. And then the episode ends when the agent correctly classifies the object in hopefully the minimum number of steps that it needs to take. And so the agent receives rewards at each time steps when it misclassifies the image or classifies it correctly. So a recent project from Facebook AI Research kind of looked into this in addition to other benchmarks. And so we are working right now just to first start out by reproducing the results using the MNIST and CFAR10 datasets. And we'll be using PPO, TRPO, as well as actor-critic methods to first try to just accomplish their results. And then after that, we want to try slightly different variations. So our initial ideas for some experiments are testing the resilience of these algorithms by using noisy or corrupted images, as well as trying video captioning, as well as trajectory imputation. So some of the difficulties that we've seen so far are kind of engineering a metric for image classification. In the case of captioning, we can use blue, but in the case of just captioning, I guess classifying things like MNIST, we're not really sure what metric to use. So, yeah.
Yeah, so some of the goals that we had for the project were, at least short term in the next week or two, were just to implement the results. We're reaching out to the authors of this work. This work was done just in November 2018. It's on archive. It's still not published yet. So we think that it still has some, we still think that there can be some progress made here that no one has done before. And we want to identify RL paradigms that work well, because in the sequence prediction application, actor-critic was identified as the most effective paradigm, but proximal policy optimization and TRPO were found to be useful in the work by Facebook AI research, so we think that's a good idea. Also, just one thing that we wanted to mention is that even though we find image classification interesting, we think that the more general object recognition is a more interesting problem, and we want to be able to extend this project in that direction eventually. So that's a more long-term goal, and we don't foresee that happening in the next couple of weeks, but we hope to be able to tackle that in the future. Another problem is sort of precisely defining the object recognition problem, because the image classification one is a little easier to define, and we don't see that to be the case for object recognition. And that's it. Thank you. These are some of the references that we based this work on.
Yeah. All right. Hi guys. My name's Connor. This is Byron. This is Rohan. And we're also working on generalizable reinforcement learning for object recognition. So our mentor is also Huang. Let's get started. So I guess the background motivation for generalizable object detection for RL is that deep RL has been very successful in the field of AI. There have been lots of breakthroughs with regards to policy gradients, actor critic networks, and so on. And it's been very successful in being able to solve like these types of like video games. So I guess many of you have heard of the Atari learning environment. These kinds of things, like deep RL has been used, been very successful in these kind of like single like constrained environment problems. I guess one problem that is still something that is an open question, but is the issue of generalization. So I guess this is the breakout game on the left. It's just traditional, like for the Atari learning environment. And if you just change the background screen, or if you just change it from black to blue, it actually doesn't, just the model trained on the black environment doesn't exactly generalize to the blue environment. So there's, I guess, lots of areas of improvement that need to be like done in this field.
Yeah, so based on, there's a little bit of research that's gone into like understanding how reinforcement learning can be generalized. Like in theory, if we kind of train, like we make some modifications to the environment while we're training, it should allow it to generalize, but like usually when they're for like standard reinforcement learning problems, like they almost always care about evaluating their agents on the same environment that they're testing, that they're training on. So in the direction of generalization, there's been some work by Zhang et al. And they suggest like a few different ways to like frame problems that are more general, and in particular, they focus on the domain of object classification and object recognition. So what we want to do is basically extend their work. You can see like this is just a digit from one image from the MNIST data set. They propose a few ideas for like treating object detection and object classification as a reinforcement learning problem, and specifically in a way that like allows us to test, is the agent actually generalizing to new images that it's never seen before. So let's quickly describe how exactly they do that. So initially, like the entire image is blacked out. It's just a 28 by 28 of all zeros. And we randomly start the agent at one of the squares. At each time step, the agent picks a direction that it wants to move in. Initially, we'll only allow it to move in like one of the 4 cardinal directions, but we can easily extend that to like allowing it to jump all across the image. Basically, as it's moving around, it'll reveal whatever pixel it's like moved to. And the goal is to try to move to as few pixels as possible while still allowing the agent to correctly classify the digit. So in accordance with that, we pick a reward that is the negative of the number of times or the number of actions it takes to get the correct classification. And then as soon as it gets that correct classification, the agent just ends.
Yeah, so like the previous group mentioned, our first plan of attack is to just implement the benchmark basic standard RL algorithms that everyone uses on this sort of environment, and we'll do that via OpenAI Gym and Baseline since it's pretty quick and easy to use. It's important to note that the idea here is not to make a good classifier, because if we wanted that, we could just use ImageNet. But we want to see whether RL can actually generalize well. So if it can have good performance across a wide range of different images it hasn't seen before, we can say that RL sort of generalizes. This is a purely experimental evaluation though. What we hope to learn from this project is whether the RL paradigm is actually capable of learning policies that are robust and not brittle. As in, we want to see if we can make RL not overfit to its environment. And since it is a deep RL experiment, the hardest problem will be kind of getting the algorithms to work, because deep RL is notoriously finicky. It takes a very long time and a lot of compute power to get even one experiment to run properly, and a lot depends on whatever random seeds we use. So kind of just getting everything functional at first is going to be the hardest part. So the goals of the project overall are to provide useful RL benchmarks on a new, more difficult task that's different from the way normal RL problems are framed. We hope to kind of lay the foundation for a new direction in generalizable RL, because the way reinforcement learning problems are framed right now is really not such a useful one. It's very specific, and it's, as the Zhang paper notes, it's not very applicable to real world problems. And we want to investigate the question of generalizability in reinforcement learning, since it's a very fresh research direction, and maybe lay the groundwork for more theoretical analyses in the future. Thank you.
So I'm Andrew Taylor, this is my partner Victor Dorobantu, and we're going to be looking at learning affine representations with specific interests in applications for control. So when you talk about control systems, you talk about nonlinear dynamic systems, and you have some state space, and these are topics that are kind of shared, particularly in reinforcement learning. You've seen them across a couple of branches, including imitation learning as well. So you have some state space, some X, some states you can lie in. You can think of this as something that you would see from a hidden Markov model. This is the state I'm in, and then you have some input space. You have some actions that you're able to take. And what you want to do is learn this mapping that goes from the states X to some output function H. Now you know that this representation is a nonlinear function of X. It can be a horrible function. For most robotic systems, it is. If you have some actuator that you're trying to move the end of, there's a bunch of nonlinearities. If you reduce f of x and g of x to linear functions, a and b, they start to look like the paradigms you see in finite horizon control and machine learning. If you've ever seen any kind of Q learning, it's using these kind of principles for propagation of the dynamics. We're interested in the nonlinear variant. What we do know for robotic systems is that the control input is an affine representation. Just because f equals ma, we get this very nice representation. And because of that, there's actually a whole suite of powerful control techniques we can use if we know f and g accurately. In reality, you don't actually know those. There's unmodeled dynamics, there's parameter uncertainty, and you want to capture those. So one particular output function we might be interested in learning, you may have heard this in the context of reinforcement learning, it's the basis for nonlinear control is Lyapunov Functions. So Lyapunov function is essentially a potential, and if you can drive that potential to 0, you achieve some control objective that you've specified with that Lyapunov function. In particular, your goal is this dVdt term here being less than 0. If that's less than 0, it decays over time, and it will converge to 0 as it's a positive definite function. So we reduce h down to being a scalar function, and we're trying to learn this representation here, the grad of v transpose f of x and grad of v transpose g of x times u. And we want to represent these with these models b of x and a of x. B is a scalar and a is a vector. Now, this is something that's particularly interesting here, is that these things you're learning are going to be used downstream for control action. And it's not sufficient simply to learn a model that predicts A and B and gives you very low loss at predicting H. If you do that, you can actually learn incorrect values for A and B. And this is a scenario such as A hat, you can learn some additional A tilde term, and B of x can learn this minus A tilde U, and you get that if your control action is deterministic. When that happens, you still get the same output, H of x, but your models are incorrect. Now, later down the pipeline, when you go to implement this on a robot, you use these models A and B. So even if the loss is low, you can still do really poorly in the control application. This is something you want to avoid. So what we're looking to do, and I'm going to give this to Victor to explain a little bit more, actually.
Yeah, so as we were saying, this term over here and this term over here, these are the things you're interested in learning specifically for control applications. We've talked about generalizability a little bit in this class and some specific kinds of notions. This is a little bit of a different one. If we assume that those underlying functions that we're trying to model are actually Lipschitz continuous, which I've shown up a bunch of times in this class, and we use some sort of Lipschitz continuous class of models, like spectrally normalized deep neural networks or something like that, what we can actually do is define a polyhedron in which these functions actually have to live. Specifically, we'll fit these models all over the state space, and then we say, okay, we achieved this loss over here and this loss over here. That means as we move towards some unseen point, we know that this whole function can't grow too quickly. Once we define this polyhedron, we can actually run a robust linear program, or we can formulate a robust linear program to pick the optimal direction in which to choose a U that will lower the uncertainty all across the state space or in regions of the state space that we really care about. That's one potential direction that we want to take this project. The other kind of involves some of the stuff that we've seen with tensor math so far. Specifically, if you think of F and G as nonlinear maps to tensors, what we're really interested in here is a contraction. Once you've mapped into that, once you've mapped from the state space into the space of tensors. So we're actually looking at applying this grad V of x term to F and to G of x. What we want to see is if we can come up with some sort of representation that isn't going to care if you add in other terms that look like this. Basically, things that evolve orthogonal to grad V of x. And I think that's everything, yeah.
Any questions?
I have a question. So is it, to make sure I understand, it's kind of like an active learning idea, right? So you're trying to pick the optimal U to learn as much as you can about the dynamics. Is that the right?
Yeah, so depending on when actually you decide to refine the models, this thing can look episodic, it can look like a reinforcement learning problem, it can look like an active learning problem if your future states that you observe don't depend on the decisions that you're making right then. So that is a particular version of this problem. I think that'd be a little bit harder to cast as a control problem, but you could still do this for any number of ML problems that can be modeled with this affine structure.
One of the really interesting parts of this is building this structure you know the model should have at the end, and like trying to capture that in a learning problem rather than just trying to learn all of the structure on the outside, starting with a really good guess at something.
Mm-hmm. Anything else?
Hello everyone, my name is Hao and this is my partner Jialin. And our topic is regularizing reinforced learning with imitation learning. And first is a brief introduction of reinforced learning. In reinforced learning, it's just we are given the environment access and we can get something like reward from environment. And our goal is to train a policy that maximizes accumulative rewards. And here are some applications of reinforced learning. It's basically about playing games. The first one is Atari games, and now the second one is Go, and the third one is StarCraft. And for imitation learning, we are given is demonstrators or demonstrations, and our goal is to mimic the demonstration, to train our policy to mimic demonstration. And it's basically like here in the first graph, we are given how to drive a car, and we are just try to, it can be think of a sequential of supervised learning to learn this policy. And our motivation is very straightforward. It's just how to trade off between these two. In imitation learning, we can have some extra feedback. It has very high quality, but it's very expensive. And in reinforced learning, the cost is very low, but the quality is not very good. And we state our problem as, besides the traditional reinforced learning setup, here we have a learning budget, which is the capital B. And every time the query, it has the query environment will have a cost per. For reinforced learning, we have a cost, and for imitation learning, we also have a cost. And here, the imitation cost is strictly larger than the reinforced learning cost. And our goal is to learn a policy to maximize accumulative rewards, which is same as the reinforced learning. And our challenge is design a controller to switch to decide every iteration whether to query the expert or query the environment. And there are some prior approaches recently. There are two papers this year. The first one is called Loki, and it basically is that this paper it casts reinforced learning and imitation learning algorithm in a framework of online mirror descent. And the algorithm it proposed in this paper is just use first k rounds of imitation learning and then followed by reinforced learning. And by using this, it can outperform both. And the second one is called truncated horizon policy search. It basically is using the near optimal cost to go as the oracle for cost shaping.
So basically our idea for the room for improvement is in general, reinforcement imitation learning, they do not consider explicitly the cost in terms of acquiring feedback. But in practice, the imitation learning application is limited because acquiring feedback from experts is very expensive, versus in reinforcement learning, you can easily run iteration in the order of magnitude of millions. That's fine because you just burn more GPUs. So that's the first thing we want to consider is to model the cost of acquiring two types of different feedback into the learning process. And the natural progression of this approach is to, okay, now if we take consideration into the cost into the picture, then each iteration we might want to switch in terms of using which kind of learning paradigm. And so in this case, we can think of the Loki, the one we just see the previous work, where they apply imitation learning for k time steps and then do reinforcement as a special case. So you can think of they just switch once and then they're done with it. So we wonder if there's a more adaptive type of switching, so we can switch back and forth between these two learning paradigms will be better. So potential approach. So we have right now we have two ideas. One is extending Loki. So what Loki is doing is they do the first k rounds of imitation learning. But in general, in imitation learning, you still need to roll out a current policy to collect trajectory samples. So you can imagine this process actually gives you also environment rewards. So what they do is they disregard this reward and just use the expert feedback to do imitation learning. So a straightforward extension is consider how to incorporate the environment rewards into the first k rounds. So and there has been prior work in terms of how to combine imitation learning with reinforcement rewards. So that can be a straightforward extension to see if that can help.
But the main focus of this project will be on the second point, is adaptive choosing reinforcement imitation learning, so that we can potentially gain faster learning progression in a limited budget setting. So ideas here is we can think of, so the paper, the Loki, they combine reinforcement imitation learning into the one online mirror descent framework. So the problem reduced to at each time step which kind of gradient information we want to use. So that can be a source of information in making this decision in terms of deciding which kind of learning paradigm we want to use. And so the plan is, as usual, for this learning, for policy learning, we'll use OpenAI Gym. So mostly it will be focused on some locomotion task on the Lojuku and some control task and this new car racing environment as well. And the challenge, well, so the challenge, the first one is obvious. And so we're interested in both the theoretical guarantees of those two, of the new designed algorithms and also demonstrating empirical improvements. And the short-term goal, well, is to design a new principal framework for trading off those two types of learning paradigm and demonstrate empirically improvements. Well, long-term goal for any policy learning is to want to deploy a real system, for example, in robotics. And I think that's all. Questions? Sure.
In this imitation learning setting, the expert, which you're going to solicit feedback from, this is a pre-trained model? Is that the expert?
Right. So in general, this we can think of as coming from some kind of human experts. But in general, but that's too costly. So we can use a pre-trained model, which we can think of as near optimal to provide feedback.
Okay, and what kind of feedback does this expert, this pre-trained
So
model
normally is, as I said, you would roll out the policy first to collect some state action. And so the feedback will be, okay, you run the expert policy on the states you have encountered and see what the expert would have done in the states you haven't done.
How to make it work? We cannot detect the display. We cannot detect the display.
Okay.
Just extra minutes.
是那个电脑。
电脑。
哪个？你是哪个？你是哪行？
是跟输入的关系，就是插画的。电脑是哪个？
考一下，你想上哪个？你不用看哪个啊？我刚刚发到了这个，这个没有了吗？就是 PPT 的呀，这个。你插上去，插哪儿？这没了，两个都可以，都没有随时都可以。
If you grew up in a team, I said we have no line, but it's easy. If you do, image, you know,
又没了。Oh, sorry for the delay. Our project is about the domain adaptation on the level shift with active learning setting, and MU, this is Shasha. The brief introduction, there are two topics covered in our project. One is the domain adaptation, and we will consider the level shift in this project. The level shift is that the level distribution, the target and source domain are different, but the distribution of x given y is the same. And another topic covered is the active learning. Our objective is to learn to optimally the machine learning job, more specifically the classification job, in target domain with the help of active learning. Why domain adaptation? This is because under some settings, the source domain and the target domain have different distributions, and the models learn from the source domain may fail to achieve good performance in the target domain. So we need to correct for the shift. This means that we need to estimate the importance weights so that we could reweight the source samples in order to get a model which is applicable in the target domain. And why active learning? This is because we consider adding some useful target level information for the estimation of the distribution in the target domain. And in the regularized learning for domain adaptation on the level shift, which is the reference provided in the project ideas, they have provided an efficient weight estimator, and we hope to extend it with active learning setting for better classification performance in the target domain. And why it matters? This is because in reality, mostly the training and testing distributions are not exactly the same. So this is the reason that we need to apply the domain adaptation. And also sometimes the target level information, they are achievable. They are obtainable, but they are expensive. There is also an example mentioned in the project ideas. This is a diagnosis problem. In this problem, we can get the target level information by sending doctors to place B, but actually this is pretty expensive, so we extend it to the cost-sensitive problem. So the problem change to how to choose the limited number of target samples to level is crucial. So in this project, they have practical meaning and values. And for the prior approaches, for domain adaptation according to the regularized learning, they have provided an efficient importance weight estimator, this to relate to the source samples. And they also provide a dimension-independent generalizing bound.
for the classifier training on the related samples. Also, they also have good performance for the small sample regime. So in all, they have already improved the classification accuracy in the low sample and large shift scale. So about the active learning, there are currently many query strategies. For example, the random sampling, core-based sampling, uncertainty sampling, and etc. So what's new? The new things in our project is simple, but it may be kind of hard to implement. This applies active learning so that we could provide more information for the domain adaptation.
Our main idea is to apply the active learning method to the domain adaptation. We want to extend the regular learning for label shift framework to the active learning setting. We want to get most information of the data distribution of the target domain by querying list labeling cost. And by doing this, we want to better correct the shift and fit target domain with lowest cost and improve the classification accuracy. The data we plan to use is a mixed data set. We will randomly separate the entire data set into two sets of same size and sample the same number of data points from each pool to form the source and the target set. Assume source data set to have uniform distribution over the labels and apply various kinds of shifts on target data set. The potential hardest challenge in our project is design the algorithm to combine results from regular learning for label shift and active learning for better weight estimation. Also, query strategy selection is also is another challenge. Our goal is first we want to compare the performance of several query strategies under domain adaptation situations by conducting empirical studies and choose the best query strategy for active learning. And then we want to design an algorithm to optimally apply active learning setting to regular learning for label shift and conduct experiments to compare the classification accuracy in target domain with regular learning for label shifts.
Any questions?
There's also HDMI.
Why isn't there a signal?
Oh, I see.
Okay, so my name is Michelangelo, this is a Tao. So we're working with, this is a continuation of a project from something we did last term, working with the seismology group at Caltech, in particular Men and, I guess his name is not up there, another guy named Zach. Let's go to the next slide. So just to kind of give like a high-level overview of sort of like the broad scope of this project and kind of like projects similar to it. So of course, there's a lot of earthquakes that happen throughout the United States. 143 million Americans are actually in areas of seismic risk, and this is where a system called Shake Alert comes in. So this is an example of what you call an earthquake early warning system that basically monitors earthquakes in real time, sends that information to data centers, determines whether or not there's like a risk for an earthquake, and then alerts nearby populations. So this is an implementation in about 3 states right now, and basically just kind of alerts transit companies and electric companies and sort of like first responders. But eventually one day you all may actually be alerted by this. So the kind of question is exactly, well, how can you sort of extract this seismic data and predict whether or not an earthquake is going to happen? So this is kind of like the physics behind that. So when a fault slips, it emits two waves. You have a P wave and an S wave. The P wave moves compressionally, and the S wave sort of moves perpendicularly with respect to its direction. So what's interesting about this is that the P wave is significantly faster but significantly weaker than the S wave. So you can kind of see here, P wave comes in nice and weak, and then eventually, in delayed response, the S wave comes in. So the idea is that you can use the P wave, because they both originate from the same source, you can use the P wave to sort of foretell what the characteristics of the S wave may be like. And this is the principle behind earthquake early warning. So these techniques that are currently in place are sort of from an era that didn't really have like much computational power. So they usually rely on regression techniques. They extract very simple kind of information from the P wave, such as the displacement period, and they also have this amplitude parameter. And then from that, they sort of like have these lookup tables, and they sort of estimate the magnitude of the S wave according to some predetermined relationships. So of course, there's a lot that can be sort of advanced with here. And the sort of kind of question that we're looking at is, can you actually not just maybe predict certain characteristics of the S wave, but can you also maybe produce entire waveforms and actually like get an entire like sample what the entire S wave will like look like in some time window. So so the data set that we're working with to tackle this problem includes roughly around 200,000 records. These have 3 channels. You can imagine you measure the velocity in 3 directions, the X, Y, and Z direction. And this is over 100 seconds at roughly 100 hertz. And then we also have metadata such as the magnitude of the earthquake, the center or sort of the origin of the earthquake, like latitude, longitude, how far away the seismograph was away from the earthquake, and then also just various station information, exactly where that station was with respect to latitude and longitude coordinates. So there's a lot that we can work here. As of right now, we're just working with a pure waveform. So
yeah, I'll continue with the approaches that we tried and plan to try. So when you met with sequence data, the first thing that will come into mind is try to run an LSTM on top of it. So basically, we already experiment with this approach. So we did a many-to-many LSTM. Basically, we extract. We first use the try to predict what's the waveform in the window from 5 seconds to 10 seconds, based on the waveform on the 0th second to the 5th second. So we run a many-to-many LSTM on this data set, and it turns out that the performance is not very good. Essentially, we are not able to extract any information from this waveform. And we kind of consult, we asked the seismologists here at Caltech, and they said basically there is some kind of stochasticity in the seismic waves, and you don't expect that the deterministic models like LSTM would perform well here. So with the aim of being able to generate the envelopes and also the whole waveform of the S wave based on the information of the P wave, we kind of think that generative models would work better here. So since we know that GANs is able to generate realistic images based on human figures and wild scenes and so on, so we're thinking about using GANs to generate, it's a 1D data set essentially, so we try to generate the waveform of the S waves based on P waves using GANs. And so here's the kind of the architecture that we experiment with at this moment. So it's taken from this paper. So it's a DC GAN that these authors tried, and we basically took their took their code and then we customized to our own data set. And we are able to generate this. So it's right now we are trying with the window from 0 to the, so it's 6 seconds of the data set, and it seems pretty realistic. And so right now we are only experiment with one component of the waveforms. Essentially, we are given a 3D waveform, but right now we are only experiment with the Z component. So the future plans would be to be able to generate the whole 3D waveforms, and also right now we haven't taken into consideration all the meta information like the hypercenter distance, like the scale of the peak, and so on. So we are able, we hope that we can include that information as a feature of our model and train the so-called conditional GANs on top of this data set. And we also want to be able to, right now we basically just input the raw waveform into our model. So we want to be able to experiment with various pre-processing techniques, and including the waveform scattering transformation that was studied in various publications. So that's our short-term goal for this project.
Thank you.
Yeah.
Any questions?
Also a question. Can you explain it? I missed the part. So what is the generator doing? What is the discriminator doing in this setting?
Yes. So the generator, what the generator is doing is basically generate based on white noise. Okay. And it's trying to generate realistic S waves that are going to be predicted by the discriminator. So that's basically what the generator is doing.
Yeah.
So the discriminator is trying to decide which S waves are real, which ones are
Yeah,
exactly.
But I guess the part I'm confused about is how does that connect to the goal of predicting S waves from P waves?
Yeah, so as of right now, we're just experimenting on a simple model to just generate S waves. Eventually, we want to move to a conditional model where we'll actually have that conditional on the P wave. Okay. Potentially, we may also have a conditional on the earthquake magnitude and the distance from like the center. In which case, it wouldn't really be that good as like a predictive tool, but it would be useful for just like simulating earthquakes for just like pure research reasons.
Hi everyone, welcome to our presentation. I'm Wengu, and this is my partner Qilin. Today we're talking about the DRGAN, which is the Deep Rendering Generative Adversarial Model. Yeah, recently generating some realistic pictures by computer becomes a very hot topic. And speaking of generate some realistic images by computer, we're thinking of GAN first, right? So on the right of the picture, it was two faces generated by GAN. And our proposed solution is that based on the GAN framework, we embedded a neural rendering model, which can be used both as the discriminator and the generator to this framework. And then our goal is to explore some new structure that which is expected to perform well in generating natural log images with high sample efficiency. Yeah, here's some prior works. As we discussed in the lecture, this is GAN. It basically has one generator, one discriminator playing zero-sum game. And another scholar implements improved version of GAN, which is the ResNet as generator and fully convolved neural network as discriminator. But there are some like drawbacks for GAN. That is both generator and discriminator still have different structures and have two set of parameters. So when we are doing training, we have to tune two set of parameters synchronously. So here comes to our neural rendering model. One scholar proposed the neural rendering model. It's an invertible deep generative model following the CNN design. In this figure, we can see that the NRM has both functions as inference and the generation. For inference part, we take one image, we classify it's some object, and from the generation part, it just do the invertible work of the CNN. It basically take one label and give you a picture of that label. When the NRM doing the inference job, you can see there is some some loss in the information in the CNN reference. So we use the latent variables to compensate for that loss, so that we have one label and by those latent variables to compensate for the loss, and then we get rendered images. And the one advantage of NRM is that it is a generative probabilistic model. It has strong ability to capture the latent space information when generating images. And also it matches the architecture of CNN. So it's instinctively a good discriminator when doing the inference. And this model can be applied as both generator and discriminator in the GAN. So one disadvantage of that is that we introduce a lot of latent variables for this rendering. So the complexity of the NRM is higher than the CNN.
So our idea, which is proposed, this approach to solve the problem is by combining the GAN and the NRM to a new generative probabilistic model, which we call it the DRGAN. Basically, we use NRM as both the generator and the discriminator. But we need to notice that since it can place the two rows, we only have to train one model at a time. And furthermore, in the long term, we may also can add some more knowledges like the graphics and the physics, so that to make the generated image more realistic. We will test our model on some traditional data sets so that we can compare the results with traditional methods. So basically, in order to complete the task, first we have to set up the GAN structure and learn how NRM generates and discriminates images. And then we would like to improve the loss function of the NRM by introducing the adversarial loss. So there are a few challenges in this project. Firstly is that by combining the adversarial loss with the traditional max-min cross-entropy loss, which basically is an MLE optimization problem. There could be some problem inside. Second thing is that the previous paper only tested NRM on the supervised or semi-supervised way when doing the inference of the image. So the result of rendering the image with NRM is still uncertain, so we still have to explore whether this is good or not. And the third thing is that because we only use one model to the discriminator and the generator, which means we have to synchronize either the parameters or the loss during the training process. So for the goals, for the short-term goals, we would like to modify the NRM with adversarial loss to improve the visual characteristics of the generated images. And after we tune the model, we're going to train it and compare it with the traditional method. For the long-term goals, we would like to also explore the semi-supervised way or unsupervised way on training the DRGAN. And we can also add the graphics and the physics information during the generating process. So, is there some questions? Okay, so thank you for
Which one of these goes? Okay, cool. Hi, my name's Ethan, and I'm going to be investigating EGANs. This stands for Elaborator Generative Adversarial Network, which I'll get into. So, background, we're all familiar with GANs at this point. The hard part is we're not really sure how to compare them. Like, a bunch of people have proposed a lot of different models for what a good generator, what a good discriminator could be, but unlike in supervised learning, it's not like a very clear loss function. You can't just like compare image and net results to compare two models. And what is clear is that your choice of what the generator and discriminator architectures are has a very big impact on the results you're going to get. And there's a whole suite of papers proposing different architectures because of various reasons. But it's still pretty unclear how to pick the best generator and the best discriminator for a given task. The idea behind this project is if you want to get the best results, like on deciding a task, specialization helps. An analogy of like going to a hospital, like if you have a very specific condition, going to the general ER doctor is not going to be as good as going to like the specialist in whatever field that you have the issue in. And so we want to be able to let the discriminator in a generative model specialize on certain types of the input. More concretely, so like we're trying to model this distribution over the manifold of like, in this case, possible images. And the classical GAN with like one generator, one discriminator says, I want the discriminator to be accurate over this entire manifold. And what we can do instead is subdivide that manifold and say, on this subclass of images, we'll have one discriminator to figure it out. On this other class, we'll have another one. And let those discriminators specialize to the different subsets. And ideally, this should help improve performance and get a better discriminator. The question is obviously, how do you divide those images? And so we use a network for it. So this is where the elaborator comes in. So the idea is in the schematic, so like you get real data, you have your classic generator, this could be whatever you want, and this is your fake data. And then to discriminate an image, it's a two-step process. First, we take the image, and we pass it into the elaborator, E, which will process it, look at it, and say, which discriminator do I want to actually use to decide on this image? So it outputs a weight vector that assigns weights to the different discriminators. And then we have a pool of, or gang, of discriminators that we pick one according to the weights, and then use that one as input. And we train that discriminator on that example only. So in this way, it's a probabilistic distribution. So the W's are weights, and it's not like a deterministic choice. It is outputting a sequence of weights, and we choose one at random according to that distribution. But we're letting the elaborator kind of partition the types of images it will see amongst the different discriminators. No, this error. So some of the key features of this, the biggest feature is that each discriminator is only going to be trained on a certain subset of data. The discriminator gets trained and has its gradients updated on the images that get passed to it. This contrasts previous works, which have also, a couple previous works have like looked at having multiple discriminators, but in that case, they train, each discriminator gets trained on all the images still, which doesn't allow for this specialization to like certain subsets of images, which is what we're going for. The idea being that in this way, because we can like split up and use different specialized discriminators, we can unlock a larger diversity of like possible discriminator functions to test on, and thus making our discriminators richer. So the work I'm going to be starting out with is working on the syllabi data set. It's a bunch of faces, but keyly the faces also have characteristics. So there's like a feature vector associated with each face of like, are they wearing eyeglasses? And like, these are just a couple of them. And our hope is that this feature vector will make it a bit easier to learn, because this elaborator, instead of having to extract everything from the image itself, will have some features that may be relevant to deciding between different discriminators already in a very clean feature vector. Also, as our initial gang of discriminators, we're going to keep it small, because don't make things too complicated yet.
And we're going to focus initially on the Wasserstein GANs, which is what we talked about last class about having a spectrum 1. That's that idea, because we found, like empirically, that those types of GANs are more robust in training. The primary challenge in getting this to work is going to be figuring out how to balance a whole gang of discriminators, an elaborator, and generator. Because now we have like, it's not just 2 agents, we have like n agents where n is going to be bigger, which is harder. And so figuring out a good search and learning strategy for the various agents is going to take some work. And goals going from there, if this is successful, it's a lot of like long-term implications. Obviously, immediately we have like code to scale up to having more models than just more types of discriminators and different types of discriminators that follow completely different architectures. And also, there's open questions on what type of search space is best for the elaborator. Exactly how much can we model the increase in functions that the elaborator gives us, and possibly even comparing discriminators. If we take 2 discriminators, put them into this gang, and it turns out that consistently the elaborator always favors one over the other, that may say something about the quality of the discriminators. Any questions? No, cool. And we're done class.